Okay, let's get started. Hope everybody's making some progress on assignment number 7. This class is largely going to be a clinic class where you can work on things, but we have a special celebrity appearance by Rachel Hegeman. Come on over here, Rachel. Special celebrity appearance by Rachel Hegeman, who's just finished your master's degree.
Not quite.
Thanks
for reminding me.
So Rachel was a undergraduate mechanical engineering student here at Hopkins, and is just finishing her master's degree, and is an ambidextrous and omnivorous robotics creator, and who also worked. I had the good fortune of having her work in my lab for a period of time, and I showed you a photo of Rachel's class here in 2016. The class was about half the size of this class, and there's Rachel and her partner Ryan. In that year, these three guys built up a car, and Rachel and Ryan also built up a car.
Yeah, sorry I couldn't carry both of them over.
No, not at all. I asked Rachel, and Rachel is currently a full-time employee at the Applied Physics Laboratory, but she actually works here most of the time on robotics projects, and her office is here in 136. Right?
Yeah, I think so.
Yeah, 136 Hackerman, which is where all the postdocs hang out. And so I asked Rachel to put in a celebrity appearance to tell us a little bit about her project that she did with Ryan Howarth.
Yeah, so this is the RC car that we built up.
Do you want to project?
Oh, I don't really have anything on my computer. It's just things to remember. So we used a lot of a design that was made by another grad student, which is Subhranshu Mishra, and he did a lot of the programming and interface design for the devices that are on here. So we basically adapted his design to do some general global planning with ROS, and then so that we could get the car to autonomously navigate to a spot that we chose. So what's on this car, we have the computer, the wireless router. Here is supposed to be a Fukuyo 2D LiDAR. And then there are, except we don't have that right now.
Yeah, if you want, Simon Leonard has borrowed it.
Okay, got
you have both of them.
Okay, I was just making sure.
So if you want to browse to this old website here, and this subpart, you'll get the webpage that I was just browsed to, and you can scroll down to a quick summary of Rachel's project here.
Yeah, so it lists some of the ROS nodes that we used that are running both on these APM boards, the two APM boards that we have right here. We only used one. On the APM boards, there's an IMU. The APM board also has
Tell me what an APM board is.
Sorry, it's this little computer right here. It's a flight controller board. Mm-hmm. And you can also do drive control with it. And so that one has the interface to the encoder and to the Futaba receiver that we have. I didn't bring it over, but we have a 7-channel controller that we use to actually send commands to the car, and we didn't want to do it autonomously. And then, so Subhranshu also designed this encoder that's down there that goes on the drive shaft, and the encoder values are useful for when we fed them to the estimator that we had, which was just the ROS AMCL node, which I think is up there.
Right, and we saw AMCL for the first time on Tuesday. We did the Turtlebot simulation with AMCL.
Okay, cool. So we used that. And then we also, so Ryan and I did a lot of work to sew that together with Subhranshu's existing interface, and then put the ROS navigation stack on top of it so that we could send it poses in RViz and then have it plan globally and then be able to control its path on this trajectory that was the plan, resulting plan. And some of the issues we encountered were the global planner wasn't meant to plan for non-holonomic vehicles, so we'd often get plans that weren't achievable. What would happen is if I'm trying to like get to that spot over there and the trajectory is like very curved like this, our local planner that we used, it would kind of go like, and then like that, because our local planner took into account the non-holonomic constraints of the vehicle, but the global planner did not. So we oftentimes got infeasible trajectories. So that's one thing that really needs to be done, is getting a global planner that obeys non-holonomic constraints. And then, let's see, the other issue we ran into, so one thing we didn't actually explore was, I think there was a GPS ordered along with this, and to integrate that into the estimation would be really great, because we tried to map outside, but when we would go around an area, such as Mason Quad, we would go around that loop and we'd come back and our map would be not adjoining, so in the same place, right? So I think integrating the GPS into that, the estimation would be really great, and that'd be cool. But yeah, there are a lot of things that can be done with this stack, and it was really cool to work with.
Not attached to the vehicle right now because Simon Leonard borrowed it to use in his class. Is a Hokuyu laser, this model right here, and it's got a 270-degree scan, and it does like 40 scans a second. Is that it?
I can't remember.
Yeah, it's a lot, and the data from this thing is beautiful. I mean, it's just beautiful.
Yeah, and so using the map generated by that, we were able to hook that up with a map server to our global planner, and that way we could make trajectories that planned along inside the halls of Hackerman pretty well. And that's, I think, you showed some videos of that, right?
Yep, and you want me to show them again?
It doesn't matter, but you don't need to.
And the laser scanner is got like a 30-meter range, and it's full daylight capable. You can run it in full daylight. You can get ones down around $1,000 that have decent range, but you can only run them indoors.
Yeah, that's about all I had to say, but let's see, is there anything else on here that I forgot? Yeah, so the GPS is somewhere, I think, back with the other materials.
In the spare parts kit?
Yeah.
So there's a whole kit of spare parts that Rachel and Ryan assembled for this.
Yeah, but it's a hefty ROS project, just because there are a lot of nodes running that need to be sewn together correctly. So, but it's really cool.
And this is it's like an i7 CPU. Mm-hmm. So it's a pretty powerful, nice i7 CPU in the box. This is the Ethernet switch. And there's another Ethernet switch. I don't remember why.
That's the wireless router.
That's wireless router. Okay, yeah, this is the Wi-Fi router. They did a really nice, borrowing from Sue Wrench's design. They could drive the car in remote control mode, just like a remote control car, and then throw a switch and the computer would take over, which is really nice when you're developing, because like the car starts heading for the stairs, you can take over.
Yeah. One other thing I remember from this video is you can see that the local planner often overestimated the steering angle, the amount by which the steering angle had to change. So some tuning with that local planner, or else substitution of that local planner would be great, because then it could actually, drive smoothly instead of going.
Right, and remember the video that we saw last time? Sorry, not the video. The simulation you're doing this week, when you drive the Turtlebot around in a simulated world, you're going to see a local map with a high resolution that is doing local planning on, and then a larger map with lower resolution that is doing global planning. So this is a design pattern that's often used in robot motion planning. Yeah,
it's a design pattern used by the ROS navigation stack, which we made use of and then substituted our own nodes for, basically, if we needed to. Because that stack, I don't think, does at least we substituted the local planner for, but. So, does anyone have any questions? Does anyone feel like doing a car project? Maybe? Yeah? Okay,
Yes.
cool. Awesome.
And here's the other video that you guys posted.
Oh, yeah. Oh, it's a little less exciting.
Yeah, I wish I had captured it. The thing that you're not seeing here is the vehicle, particularly when they were driving around and making maps, is watching G-mapping sort of build this beautiful map.
Yeah.
And then when the odometry is good enough, when you come back and see the same thing twice, it locks together. And so Rachel and Ryan had made some really nice maps of Hackerman using this laser scanner in the car.
Yeah.
So it's pretty impressive. Questions for Rachel? So Rachel has kindly agreed to serve as a celebrity TA for the second half of the course. And I'll see if I can hire a little bit of time of Sue Branches to provide support on the part that he designed. So they know more about these cars than I do. But I know that the components are all excellent and it's a good design. Yes.
Question. Can I ask the speed limit for this car and the turning radius?
The speed limit, it's something low. It used to, it's done that way on purpose, right? Because we didn't want our car zooming off and not being able to catch it.
The car is capable of going at an insane speed, right?
So yeah, so me and Ryan actually put together a thing. It used to be that this car could go like 40 miles per hour, but that is no longer because it's no longer using its built-in controller and stuff. So I think you can probably command it to pretty high speeds, but you don't want to because there's a lot of equipment on here.
Okay, and what about the turning radius?
The turning radius is pretty, I think it's like 2 meters or something. 3 meters, does that make sense?
Yeah, it was like 2 or 3, I think.
Yeah.
It's pretty tight when you're hard over, when
Yeah.
the wheels are hard over.
So yeah.
Thank you.
Any other questions for Rachel? Thank you so much.
All right.
I know you're crazy busy this week, but I really appreciate you
Yeah, of
doing
course.
that. Do you want us to shut this back to the lab for you?
Oh, it's fine. I'll carry it. This is why I wanted the batteries, so that I could drive it over here instead of having to carry it. But yeah, we'll have to pick those up.
Thank you so much.
Yeah.
So, yeah, those were great projects. This is the old course webpage, and I love this photo. We're going to take a class photo, by the way. So I'll give you some advance warning. That was everybody. And this year, Rachel and Ryan did one of the car projects, and let's see, Farshid was TAing, and this year, I'm trying to think of who else TA'd. I think it was Subranshu was the other TA. So that's one robot that's available, and the other one that I've mentioned before is an Open ROV, and you can Google OpenROV.com. And so this is a company it's a for-profit company, but they've started with the notion of building an open source robotic kit. And so this is their first generation robot, the so-called OpenROV 2.8. And they built and sold these things for a few years until they realized that they were still very poor. And they're about to release a new, more capable underwater robot called the Trident. It's not actually available yet. And it's got a higher price point. These things are under $1,000, and the Trident has a higher price point, and it'll be more capable. It's a pretty clever design. What we have is two, it's all made out of plastic, and so we have two battery houses here with batteries that are sort of C-cell size, and they're lithium polymer, and really low cost hardware. And they very cleverly, rather than having high pressure connectors, they actually use some clever use of glue to make a pressure barrier between one atmosphere inside the housing and the higher pressure outside the housing. This vehicle, I forgot the exact depth rating, but it's probably only good for 10 meters or so, maybe 20 meters depth. You'd have to check the spec sheet. The main pressure housing is a cylinder of acrylic, and the motors, there's 2 horizontal motors here and 1 vertical motor, and so it's not actuated side by side. And this is not a non-hollow system. It's not a unicycle because it can actually float sideways. It just can't drive sideways. So this is technically is an under-actuated vehicle, so it's different than non-hollow. And you can see that if I ask you to go forward or backwards, go up or down. Drive propellers. It does have, it has a bugle bone black. It does have a heading sensor, so it can do a pressure sensor. So it can do auto heading and auto depth. It can do auto head swap. Yes.
Does it float?
It's neutrally buoyant. And so normally with a vehicle like this, you trim it so it's slightly positive. So you trim it like so that it's maybe 1 Newton positive, something like that.
So you will come back to the surface?
Yeah, and you can always yank it back to the surface with a cutter. And this is a crappy camera here. I say it's a crappy camera because it's got what's called a rolling shutter. And that means it doesn't take the image all at once. It takes the image a little bit at a time. And so it's useless for taking images of things that are moving. So that was a bad design choice. And in this unit, the servo has been removed, I believe, but the mounting, the acrylic piece that the camera is mounted on is designed in standard design to be a servo that can point up towards the sky or down towards the bottom. And what Laughlin and Chariar did is they took out the crappy camera and they put in some small machine vision cameras and actually put in an extra bugle bone black to just push images. And the designers were very clever. They used, you may have seen advertised, you can get these things that you plug into a wall socket, like down in your office, and you plug in a wall socket up on the 2nd floor, and it injects Ethernet over the power lines in your house. So what the designers did is they hacked that. They took basically the data over Ethernet, and they figured out that you could put data over a twisted pair with no AC power on it. And so Ethernet is running over this twisted pair line. You can see there's like 100 meters of cable there, and the way you turn this thing on and off is when this little box up here applies 5 volts to the twisted pair, and that sends the signal to the relay to the robot to turn it on. And when you disconnect the telemetry wire, the robot will shut itself off. So the camera, it's got lights. Face. And so this is the console. So it serves a web page, and the way you connect to it is Ethernet here. You have an Ethernet cable that plugs into your computer, and it's serving the 192.168.254 subnet. So it runs a DHCP server. And so I've just web browsed. This is the IP address of the computer with that bugle bone black, and it's got Apache running and it's serving this thing. And you can see that the vehicle is pulling 0.9 amps. The battery is at 9.2 volts, which is 61% of the gas tank. This is the ping round trip millisecond time, and whether the connection is live or not. And it has a touch screen interface, so we can go up, down. We can turn on the lights, turn off the lights. We can turn on the double spot beam laser. And in oceanographic applications, it's very common to have spot beam lasers. And these ones look like they're 10 centimeters apart. And the idea is that you get 2 dots that when you're looking at things in the natural environment, it's really hard to figure scale because you've got nothing to compare to. And so our experience is terrestrial experience. And so when you're looking at like a tube worm on a hydrothermal vent, there's nothing there that looks familiar that can give you a sense of scale. And so the double laser spot beams are a good way to do that. And especially if the lasers are running parallel to the axis of the camera view, then you can get a good sense of size on things. If the tilt platform was installed on this unit, then we press these buttons over here on the right, we tilt the camera up and down, but in this particular unit it's not. And the little scroll bar here gives a bunch of internal data for the vehicle. So you can see it's got a heading sensor, the yaws 254, and the compass is displayed here in the bottom of the screen. And what Shahryar and Laughlin did was to develop a ROS interface node that runs on the machine, and it exposes and publishes a modest set of topics of the internals of the vehicle, and it subscribes to topics so you can send commands to it. Sorry, I don't want to cough. So, any questions? We have 2 of these, and they're cheap, so if we need more, we can get them. They're under $1,000 each, and so that's definitely well within our range. Questions? A robot with lasers on its head?
Potential applications, like potential additions, they have
Yeah. So they got as far as they built the robots from kit. They figured out how to install ROS on it. The distribution that, so I'm logged on to the CPU right here. The distribution that, it's very similar to the environment that you're running on the Edumip. They're using the Debian distribution. And so what they did was, there's no binary installation of ROS for Debian. And so they did a source compile, which is easy to do. Basically, in order to do a source compile on the BeagleBone, you need to be running off of a memory card rather than the internal memory card of the BeagleBone, so you've got enough disk space. You need more than 4 gigabytes. So any memory card that's bigger than 6 gigabytes will work. Then you need to enable the swap space, and I can show you how to do that. And then you download all the source code for the ROS system, and then you hit make, and you come back 26 hours later, and ROS is installed. Somebody was talking, sorry about that. And then you go to an installation of ROS, the current release. And they stayed with Debian because all of the existing OpenROV stuff works with Debian. And so they got as far as, they made a ROS interface, number 1, and number 2, they were publishing the topics of the vehicle, and they could command the vehicle, and they were also publishing images from the higher quality camera that they installed in the vehicle. And then they used Daniel Kremer's visual odometry package to navigate the vehicle using just unstructured things in the environment. And I think I showed that video recently. We saw the vehicle driving around in the pool, and you saw the RViz representation with feature points in the pool that were identified. And eventually you could see the features were all on the outside on the wall and floor of the tank. And then it also estimates the vehicle's motion with respect to those fixed features. So, and I thought that was a pretty impressive accomplishment, given that they started from 0. But they also did kind of the heavy lifting. So there's a ROS interface available, and there's they've figured out how to put extra cameras in this thing. And so if you wanted things that you could do, you could actually do some useful work. You could put a hook on the front of the vehicle and make some objects that were in the water tank that had some sort of a visual feature, and have the vehicle go and find them, pick them up with a hook, do some simple non-prehensile manipulation. By non-prehensile, I mean prehensile manipulation is where you've got opposing thumb and forefinger, but you can do non-prehensile manipulation by just picking things up, right? And so you could do some sort of system which picked things up and dropped things off, which went out and found objects of certain ilks. And, yeah, I mean, any sort of a navigation thing would be interesting.
The PC subscribes to the images that are sent from the
Yeah, so in an application like this, I would count on the BeagleBone to do as little actual compute processing as possible. I would try to push as much as I could over the Ethernet so that your PC with its good CPU could actually do any sort of CPU intensive image processing.
And is there any sort of speed that you can subscribe to those images? It's pretty fast because it's gauge.
I don't remember what the bandwidth of the Ethernet over the wire is. I know it's probably in Laughlin's report because he's pretty careful about those things. So I'm sure they did a bandwidth test. And these multi-drop Ethernet over a power line are pretty interesting because it's a half duplex channel. Only one Ethernet client can be transmitting at a time, and so these things run a proprietary protocol where you can put you don't have to have a switch. You can just put as many clients as you want on the same line. And it somehow handles probably with doing collision detection and random retry. It handles the sharing of the channel. So I think navigation would be interesting. Actually doing some quantitative navigation. If you did put a stereo camera pair and generate and fly over the bottom and generate a three-dimensional map of the bottom. And then you could use something like and that would be very useful because that's actually a scientifically useful thing to measure the hydrography of an area. And even better yet, if you can texture map the images over the hydrography to get a three-dimensional representation, that would be awesome. Coming up with some kind of object manipulation thing. There might be something, we could probably think of some things that one could do with two vehicles where they might be able to do some cooperative manipulation. I have to think about what that would be, but put some sort of object in there that somehow gets cooperatively manipulated. That would be neat.
If it was on the water, can it take anything off the water?
The vehicle is neutrally buoyant, and so when you thrust up with the vertical thruster, it breaks the surface, but it doesn't rise out of the surface. You could certainly add structures to the vehicle, so if you wanted to, so that if you wanted it to be able to poke an antenna up into the sky, then that's certainly possible. And we have a water tank that's available 24/7. Software resources. Yeah, so this is our water tank. It's about 8 meters in diameter and about 4.5 meters deep, and it's got a nice place to work over here with places to put your computers, and over here in this little corner kitchen, there's a really nice espresso machine. Quite a nice one, I must say. And this is another view of a part of the test tank. Other questions about the Open ROV? Okay, let's see. There's a team that's interested in, that's already kind of forming itself, that's interested in potentially putting together an entry for a robotics competition that's going to be held in May at the International Conference of Robotics and Automation in Brisbane, Australia. And so I invited them to give a little presentation on what they have in mind. And I think it's still in its fairly formative stages, but they'll tell you about that. And rather than waiting for 2 weeks to go by, because if they're going to pull this off, they need to sort of like do it now. I encourage them to give a pitch about their project now.
Deathmatch battle competition held by DJ Dodger. And then this year, they're collaborating with IEEE. So they're introducing this new robot AI challenge, in which they will be held in May at ICRA in Brisbane, as our professor introduced. In the competition, each team is asked to develop 1 to 2 automatic robots that can move on its own and can shoot projectiles on its own. And robots will compete in an arena which is pretty limited and is filled of obstacles. The purpose, the object of all this competition or task is to shoot at 2 officially controlled and programmed robots developed by DG, and each robot has a certain HP. And every time you hit opponent robots at a certain area, a certain amount of damage will be done to that robot. And your score will be calculated based on how much damage you dealt and how much damage you received. If we move on to the next page, as you can see, the robot is shown on the left. That is exactly the robot will be used and will be faced in the competition. On the right-hand side is a floor diagram of the arena. As you can see, it's a 5 meter by 8 meter arena, and those blocks, squares, means different areas or obstacles. What we have right now is when we receive the robot, as you can see right here, provided by DJ, and we have our some hardware we purchased on our own.
So you've already received the vehicle?
Yeah, we received the vehicle.
So we submit a technical report and like kind of proposal, and we want their sponsorship, which is just a robot we have here. And also we purchased the Jetson TX2, which is the computing platform that we're gonna run ROS on. And also we purchased LiDAR for navigation. That's
Yeah, so basically, they asked you to build your own robot, but since our proposal that we shall work on got admitted, so they gave us a robot. But we also have to buy other stuff if you want to put extra parts on the robot. And we're currently on building a simulation for the arena and the robot car so we can train our model, or train our strategy algorithm. And what we need and what we are trying to recruit from you guys. First, we want you to have experience in simulation in Rust, so that requires skill of writing basic packages in Rust. Second, we would like someone to have that has experience with computer vision. So the way we detect the enemy robot is on each robot you have this referee module, what they call it. So it's basically a pad which can sense impact. So when you hit someone or when you get hit, it will realize this rebel is hit. And you'll also have 2 LED lines on the edge, and that's usually that's how we picture we will sense the enemy robots. And you can show different colors, so you can distinguish between your teammates or the enemy. And we will also like an AI strategy team, which will be in charge of the deep learning or reinforcement learning to develop the actual control algorithm for our robot. And there are certain rules for the competition. If you're interested, please talk to us after the course. About the timeline, on April 10th, we'll submit our final technical report, and we're working on that right now. So that will not be one of your responsibility. We will most likely take over that. And the actual competition is in May, as we already talked about. So everything has to be done before that. Yes, because we don't want to embarrass ourselves. And here's our contact info. Please just talk to us or write this down if you're not sure. You can contact either any of us. But yeah, that's what we have for our project.
If you email me if you email me these slides, I can distribute them to the class. How does that sound?
Got it.
Okay.
Do you want to add anything else? Or do you guys have any questions?
You need one more person.
So what is it?
So you need one more.
No, we are looking for multiple.
Right, so my understanding is that you're interested in having members on the team who can help with
Yeah.
robotics, and then specifically with computer vision and specifically with machine learning, is that correct?
If you have expertise in any of those conditions or requirement, what is it?
So like
Please.
experiences.
Yeah.
And you'll be faced with a bunch of problems that are basically robotics problems, path planning and
Right.
things like that. You're planning on using computer vision as a primary sensor to sense the
Any robots.
right.
And we'll probably rely on the lidar to detect the.
There will localize the robots, many on the LiDAR.
Mhm.
Yeah.
And what lidar did you get?
Yeah, we got a pretty cheap LiDAR, RP LiDAR.
Indoor.
Yeah,
Yeah.
indoor.
Yeah. How much?
Like 300.
Yeah, they're coming down in price. That's great. Before you go to the competition, make sure you save it, buy a spare.
Yeah, sounds right.
And I'm sure that for a project like this, I'm sure that LCSR can contribute to help you pay for equipment and things like that.
Sounds good.
But I doubt that LCSR could afford to send a dozen students to Brisbane.
Yeah.
Although it's a great idea, I wish we could.
We'll see. If we do well this year, we can talk about that next year, maybe.
Right. And do you guys want to? Does everybody know what DJI is?
Yeah.
So some don't know. Could you explain a little bit?
Yeah, DJI is, in China it's called Dajiang. It's a drone company which is growing rapidly in the drone and like photography area. So they held this competition since 2015.
Yeah, but this time is, before it's just robotics company, but now DJI made it about artificial intelligence.
Right. In previous year, they asked each member in your team to control each robot. But this year, this AI challenge is totally new. So, and that's what we're trying to tackle. Because,
And so, for the last decade, there have been a bunch of different companies that have been vying to own the drone market, and DJI killed it.
right.
They have like 60 or 70% of market share worldwide in drone, some insane fraction.
Right.
And they're a very technically aggressive company, and also, from a business point of view, very aggressive. And their stuff works. That's why they're successful. Could you tell us a little bit? So you articulated what role you thought the computer vision would play, and that you thought that the laser scanning and odometry would form the basis of sort of the navigation. Where do you see the AI or learning playing a role in the project?
Yeah, I think the AI is mainly for the strategy of the robot, how it reacts to the opponent, how it seeks to win the game.
Since we're given a very specific formula to calculate the score for your task, so based on that, we can basically train our model, like rewards and penalty, so that we can achieve sort of the maximum, the optimal action to take at a certain moment, because it's totally autonomous. So after you put the robot on the field, there's nothing you can do. You control it. So we imagine we'll need some strategy to command the robot, and that's where we think the AI will go.
And do you have a place to work? Yeah.
Sort of. We will just keep working in our labs.
Space at Hackerman.
Okay.
But we will probably need some test field.
I'll find some space for you in Hackerman, okay? I'll try to do that. If you send me this slide set, it'll remind me. I'll ask the office to give you access to my lab pod in Ackerman, and you can use that. And if you stop by tomorrow, I can take you down there and show you around. Okay.
Awesome.
Questions for the team?
What's the processing power and the machine learning planning?
Processing power.
Yeah, we have to use something like a deep network, you require a lot of memory and...
Yeah.
Yeah, but we have a way that TX2 computer, if you Google that, you'll find it's a pretty powerful platform. Well, it has the way that GPU inside the I think it has 236 cores. It's pretty powerful.
Interesting. Any more questions? Yes. How are we going to use the machine learning? First, I think we'll use the simulation.
Yeah.
Well, what do you want to like learn?
Basically, we're trying to learn what is the optimal.
This is the module you're using, isn't it?
Yeah.
Yeah. We're trying to learn what is optimal move or action to take at certain circumstances. It's like playing a chess game, right? So, yeah.
So like there being a lot of study on like research on reinforcement deep learning to like implement that into like end-to-end control.
Yeah.
So I think that's like the hardest, the challenge.
Have you heard of the AI which can play Dota? So it's an AI which can play video games. So it's pretty much like it.
How many GPUs do you have on that?
Yeah, we just max there, but where is this?
Yeah.
TX2 model.
It's a pretty impressive little machine. It doesn't draw much power. It's got a quad-core ARM main CPU, and it's got 256 CUDA cores. Not a bad little device, and it's like this big. And it's
Yeah, we haven't decided yet, but I personally prefer PyTorch.
Yeah, that's what we need to look into.
Other questions for the team? So this is an example of a project that was sort of already begun, but if anybody's interested in talking with the team further about possibly using part of this as your project in this course, then that would definitely count. And the important thing is that each person have a specific responsibility, so that they can say at the end of the project, here's the thing that I contributed to the project. And remember that design competition projects like this, oftentimes when you get into them, you really don't know how you're going to solve all the design problems, and that's part of the project. Sometimes it takes some prototyping and experimentation. And in the case of machine learning for this kind of thing, I imagine that simulation will play a very prominent role, because what you can do is you can set up a gazebo simulation that will run for an entire week and run 500 or 1,000 simulations, and then you'll label them and decide which ones had good performance and bad performance. And once you have a labeled data set, then you can go to town on machine learning.
Yeah, we are. The mechanical side is pretty full right now. We have enough mechanical engineering, so we're really looking for more software part, as this course is robot system programming.
Okay, any other questions? All right, thank you guys. Okay, I think that's it for the formal part of the course. Are there any other questions before we wrap up this phase of today's class? Yes?
Homework 7, the assignments, you guys just demo it, and then
I think I asked you to demo it, did I? Good question. So the question was, do you have to demo homework 7? I thought I did, yeah, demonstrate. Yeah, anytime. You know, office hours, or before or after class.
Like, with the previous homeworks, you know, things always do, that spring break.
So it's not, so this is due after spring break. I think I had hopefully I got the date right here. Assignment number 7.
Listen, but I guess
Oh, I didn't put the date in here, did I? I'll revise this. So this is due the Tuesday after spring break. Due the Tuesday after spring break. And I wanted you to be able to work on this over spring break, something that you can just run in simulation. And I want you to take some time with it. Don't just like, because the actual assignment is pretty trivial, but I want you to experiment with things, try different things out, fool around with the parameters in the G-mapping algorithm, and the AMC algorithm, you know, prospect on targets, topics, make a better map than I made in class the other day, like actually drive around objects and get a sense of how hard it is to do loop closure and things like that. So it's a good way to get started, and this gives you a taste for things like SLAM navigation, to generate a map online. It gives you a taste of adaptive Monte Carlo localization within a fixed map that you know a priori. And it also gives you a little bit of experience using MoveBase, which is a motion planning package that does both local and global planning. And there's a lot there, but these are all things that I know that you've learned about bits and pieces of them in other courses at this point. And here's a case where you can actually apply it. And there are fairly sophisticated packages that are out there, so you don't have to write it from scratch, which you don't want to, believe me. Questions? All right, I'll update the webpage with the due date for assignment number 7. Okay, rest of this class is a clinic, and I'll be around tomorrow, and I'll be away most of next week, but the TAs will be here, so if you have questions next week, then feel free to email the TAs and me, and if we can solve your problem via email, we will. If not, the TAs will see you in person. So the rest of this class is just a clinic, and I'm happy to answer any questions you have.